have discussed various types of partial differential equations. Now our next objective will be to go step by step towards solution of the different conservation equations. To do that, today we will learn one particular principle which we can use, and that principle is nothing but error minimization principle. So it stems from the fact that if you have an approximate solution of a differential equation, remember that we are not really looking for analytical solutions through computational techniques. So anyway we are looking for some approximate solutions. So when we have an approximate solution, the approximate solution will involve or incur certain errors, and a very good approximate solution will be that one which in some way tries to minimize the error, and that is why error minimization happens to be one of the key principles based on which many of the numerical methods are founded. Before going into that details, we will first look into one important consideration of error minimization principle, and that comes through the consideration of variations, and we will do that with a brief introduction to the calculus of variations. So we will not formally try to learn the in-depth understandings of calculus of variations, but we will do that to whatever extent it is necessary in the context of this numerical solutions that we are going to learn in our subsequent lectures. Let us say, let us start with an example. I mean, we will not formally start with the rigor, but we will start with an example and see that how we can come up with a rigor through that example. Let us say that you have 2 points A and B. These are 2 points. The objective is to find out a path that is the least distance between A and B. So you can go from A to B in various ways. This may be one path, this may be another path, and of course all of us know that the straight line path is the shortest path. But how we can formally pose this problem? So let us say that this is a xy plane. So you have this as x axis and this as y axis, and let us say that we are interested about the total length from A to B. So if you take a small length, let us say, let us take any of the curves. Let us say that we take this dl. So once we take this dl, let us say that we are interested to find out the integral of the dl from A to B, which gives the total length. So as we can write, dl is square root of dx square plus dy square, because for a very short length the curve is almost like a straight line. So it is sum of by the Pythagoras theorem you can write this as the sum of dl square as sum of dx square and dy square. So you can write this as square root of 1 plus dy dx So we use the short notation like y dash equivalent to dy dx, y double dash is equivalent to d square y dx square, like that. These are the sorts of notation that we will be using, which are anyway common notations in calculus. So our objective is to first find out what is the total length, that is integral of dl, which is integral of this one and the problem statement therefore becomes find the path AB that minimizes L. That is the formal problem statement, or that means here equivalently it minimizes this integral this integral involves some function which in general could be a function of x, here x is not there, but in some other example x could appear, it could involve y, it could involve y dash, and it could involve even higher order derivatives. But let us just consider the case where this function itself could be a function of x, y, y dash, out of which x is the independent variable. We can clearly make out that this y and y dash, these are themselves functions of x. This is the independent variable. Thus, capital F is a special type of a function which involves other functions. So, it is a function of some function, because it is a function of y or y prime which are themselves functions of x. So, these types of functions which are themselves functions of other functions, these are called as functionals. So, this is a functional. In a simple way, it is equivalent to function of a function. Of course, one can give a more formal definition to a functional, but let us try to just understand it in a simple way. So, what is our objective? Our objective is to minimize this integral I. So, let us now try to formalize the problem through this example and say that minimize Now, how do we minimize it? There are different ways in which one can do. So, here what we will do is we will take a first order variation which we will symbolize as delta on I. So, what is this delta? This is like an arbitrarily small virtual change in I, just like you have a similar concept in terms of virtual work in mechanics, that you have a virtual displacement, that is a displacement which is not really taking place, but it could have been allowed consistent with the constraints of the physical system. So, similarly this is a virtual change in I which we symbolize as delta I. So, how can we write this? Remember, f is a function of these variables, out of which we can have virtual changes in only dependent variables. We cannot have virtual changes in independent variables, because let us try to understand this carefully. You are changing x, and that is really a differential change by which you are going from a to b. So, dx 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 in this way. So, for each and every change in x, you could have different possibilities with changes in y. So, your y could be this, it could even be this, it could even be this for a given x. So, if your actual path is the straight line, any other path is the actual path plus a variation in the actual path. So, if this is your correct y, then you can call this as an equivalent delta y if this is small. So, you are having a small y possible, and if you now account for the fact that this is a variation over the actual solution, you can minimize this one and come to the actual solution, which is the straight line path. So, you can have variations over y. Similarly, you can have variations over y prime, but you cannot have these variations over x, because x is the independent variable. You are changing x as per your wish and then seeing what is the corresponding variations in y and y prime. So, keeping that in mind, you can write this as remember that these operators del and delta, these are mathematically behaving in a similar way. So, in fact d, del, delta, all those mathematically behave in a similar way, they are conceptually different, just like d is the exact differential, this del is the partial derivative and this delta is a virtual change. So, these have different physical meanings, but mathematically these may be treated in a similar way. So, that is how it is, just like the rule of partial derivatives that what we have used, instead of dy it is delta y, because these are virtual changes. Now, what we will do is, remember this integration is from a to b from the for the two endpoints. So, what are the boundary conditions which are there? The boundary conditions given are that at a you are having a specified y, at b you are having a specified y. So, your problem is tied down with these constraints that at these 2 points your y is specified, that means the variation in y is 0, there is no variation in y, that you have to keep in mind. So, delta y is 0 at a and b, that is in this example. Of course, in other examples there could be other types of boundary conditions that we will see subsequently, but this is one of the simple type of cases. Now, what we will do is, we will try to simplify the second term by doing integration by parts. This is the first term, and then for the second one we will consider one as something as the first function and something as the second function. So, first function should be such for which you will calculate the derivative, and second function which you will integrate. So, this is the first function, this is the second function, because from here we want to bring down from y prime to y. So, we want to reduce one order of derivative, and that is why this is the second function. So, let us write that first function into integral of the second, minus integral of the derivative of first into integral of the second. Sorry, into delta y times dx. So, you can see from this example that this d and delta, they are sort of commutative. So, it is delta of dy dx. So, that you can write as if d of delta y delta x, like that. So, you can interchange d and delta, that is very much possible. Now, next what we will do is, we will use the boundary condition. So, we are minimizing this subject to what constraint or boundary condition? Y at A and y at B specified. since y at A and B are specified, you have delta y at A and delta y at B equal to 0. So, this term will be 0. So, you are left with what? You are left with delta I equal to this one, and for minimum I, it could also be for maximum I, whatever. We generally can say that for extremization of I, it could be either maximization or minimization, you must have delta I equal to 0. Now delta I equal to 0, and that has to be true for any arbitrary, delta I equal to 0 has to be true for any arbitrary delta y. When is it possible? It is possible only when the integrand itself is 0. Otherwise, it is not true for any arbitrary choice of this delta y. So, for minimization of I, you must have delta I equal to 0. That means essentially right. So, this equation is known as one of the constraining conditions for extremization of this functional and integral of this functional, and this is known as Euler-Lagrange equation. Let us try to apply this Euler-Lagrange equation for the minimization of the distance between the 2 points, this example. So, in this example you have I is equal to that means f is equal to so partial derivative of f with respect to y is 0, partial derivative of f with respect to y prime and essentially the Euler-Lagrange equation for this case will imply that you have d dx of y prime by square root of 1 plus y square is equal to 0, because the second term is only there, the first term is trivially 0. So, the second term is 0, that will mean that y prime by 1 plus y prime square is a constant, which implies that y prime is another constant. So, let us say that is C, that means dy dx equal to C. that shows that the path is a straight line, because straight line is a path for which dy dx is a constant. So, with this background, let us try to maybe work out one or two additional problems to illustrate the use of similar principles. We stop here for this class. Thank you.